now that you've made a guess, let's try to see what happens with a couple possible models. So the first thing I want to try is just including the two predictors I mentioned along with their interaction. Okay, so I'm going to say, hey, I bet the mean of speed can be predicted with some intercept plus some coefficient times year. Year is a continuous variable here, plus some coefficient times fast, and this is actually an indicator for fast versus slow, right? So this variable is equal to 1 when the track is fast and 0 if the variable is slow, plus some coefficient times year times fast. I'm going to try putting in the interaction. Okay. Now, what do you notice already by looking at this? Well, one thing I notice is that the coefficient for the interaction when I fit this model is very close to 0, right? Which tells me that that interaction maybe isn't there. In other words, maybe I have two parallel lines, pretty much. Maybe it's pretty much the case that speed, I don't know, maybe increases with year for slow and increases with year for fast. And maybe those two lines have the same slope, right? Which would be this line. Again, what this model implies is that the slope of speed on year is 0.023, and the difference, the vertical distance between those two lines is 16. Okay, and here's the interaction. So I can draw that line. Now here, the interaction wasn't exactly 0, right? So you can tell by my plotting these predicted values, these lines are not perfectly parallel, right? So we don't love this model, maybe. Looking at the data, why not? Well, when I look at this, what I see in particular, if I focus only on the orange lines, and the orange dots, and I see how they compare to the predictions for the orange dots, in other words, the predictions for slow, what I see is that for the lower years, a lot of the time those predictions were are too low, and then I get to this middle range, right, 1940s, 1950s, when the predictions for the slow races are, let me make sure I'm saying that clearly. In these earlier years, the data points are below the predictions. In these middle years, the actual speeds of the horses are above the predictions. And then for the more recent years, the actual data points are below the predictions again. In other words, it is not true for the slow track conditions that the residuals are equally likely to be above or below the line within each year. And I actually see the same thing for the blue dots, right, for the fast. I see that in these earlier years, there are more blue dots below the line than above. And then these middle years, there are more blue dots above the line. These later years, there are more blue dots below the line, right? I see this kind of curve pattern here. And that tells me that maybe my linearity assumption is not true. In other words, maybe a straight line is not good enough to describe this data set. And another way to think about that is my normality assumption is not true, because it is not the case that given a condition and given a year that the data points are equally likely to be above or below. If you tell me that we're talking about maybe the 1960s, I'm going to tell you that I'm pretty sure that the actual data point is going to be above the prediction that this model gives. So this model doesn't fit. So what are we going to do to improve it? Well, before we do that, I want to show you the residual versus fitted value plot. And what I've done with this particular residual versus fitted value plot is something that I don't usually ask you to do, something that we don't always do, which is I have colored the points according to their different predictor values. And I'm doing that just to point out that actually the assumptions we're checking in the residual versus fitted value plot should be true within every subgroup based on X, right? So we usually check the residual versus fitted value plot to see, are the points on average follow this line? Do they tend to be evenly dispersed above and below the line? Is the amount by which they're above and below the line the same all the way across? And all those things do have to be true, but they also have to be true within different subsets. And if there are a lot of predictors, there are too many different subsets to check, but here there are not too many predictors. So what I've done is I've continued to color the data points, orange for slow and blue for fast, but I've also taken the continuous predictor of year and just dichotomized it. I split it up. So I have solid dots for years, dots representing years that are before 1960, and then these diamonds, these kite symbols for years that are after 1960. And so now I can look, and what I see here, for example, is that all three of the slow tracks for years after 1960 have negative residuals. Now it's only 3, right? But that's something, right? Those residuals are not evenly dispersed. Okay, and if I look at these orange dots here, this is slow before 1960, Maybe if I look only at these early ones, they're kind of evenly dispersed, but when I get to the higher fitted values, my orange dots are always above the line, right? My residuals are always positive. So the line is telling me where the dots would go if I had 0 residuals, but this is telling me that my predictions are too low. The data points are higher. If I look at the blue as a whole, I have this curvy pattern, right? I have this pattern that suggests that the mean residual given any fitted value is not right at 0. And if I look at either one of these, just the before 1960, the post 1960, again, I see this kind of slanted pattern in the residuals. And that is not what you want to see. What you want to see is that for the data set as a whole, and also for any particular subset of the data, that given a fitted value, the amount by which the points are above or below the line is about the same all the way across, right? But I don't see that here. I see a lot more variation among these fast dots than I do among, for example, these particular slow dots. You want to make sure you don't see any kind of curved patterns, but I do see that here. And you want to make sure that it's always the case that you have approximately normal residuals, which means that for any fitted value, you want those residuals to be equally likely to be above as below the line. And that is not what I see here. Now, I'm discussing this a lot because I know that it takes some experience and practice to be able to recognize a good residual plot versus a bad one. This is actually a really bad one, right? I know we often say that, oh, if the points are kind of randomly spread around, the residual versus fitted value plot suggests it's a fine model. But when I look at this plot, what I see is a parabola. What I see is subsets of points that are clearly above or clearly below. I see these kind of diagonal patterns. I see points that are much more dispersed in certain places than in others. Even if you look at like the variation of the post-1960 blue dots versus the pre-1960 blue dots, the variance isn't the same, right? So I'm getting worried about this model by looking at this plot. So what I'm going to do is try making a parabola, maybe making a couple of parabolas. I'm going to continue to have an intercept and I'm going to continue to have a slope for year, but I'm also going to put in a square term for year. And I'm going to continue to put in fast, and let me put the interactions too, right? So maybe my two parabolas don't have to be parallel to each other. Although it kind of looks to me like they should be, right? Like what I see is, look, a parabola describing the relationship between speed and year for slow tracks. And I see another approximately parallel parabola describing the relationship between speed and year for fast tracks. So it looks to me like I need the parabola. It looks to me like I need this year square term, but I'm not so sure. And I definitely need the fast term because it's an intercept change. But it's not obvious to me that I need these interactions. It's not obvious to me that the curvature of those parabolas are different from each other, at least from looking at the picture, that's not obvious. But if I do fit these models, well, this is a 0 because you get a really small number that rounds down to 0. If I draw those dots, it looks like this. And I would argue that just looking at the scatter plot, and again, comparing it to this one, right? This looks to me like a model that does not fit, and this looks to me like a model that does fit. To put these points on, what I've done is added points to my plot where the X coordinate is the year and the Y coordinate is the fitted value. Now I'm going to look at new residual versus fitted value plot. What I'm arguing to you here is not that this one is perfect, but that it's way better, okay? So do you see how these blue kites now are in this nice vertical strip? Remember how before they were slanted like this, right? In other words, for slightly smaller fitted values, the residuals are usually positive, and for bigger fitted values, the residuals are versus negative. That's no good, right? Where are those points? Let's remind ourselves what those are. Those are the fast post-1960 data points. So if you look here, it's fast track post-1960, okay? It's all these data points up here, and it's now the case that those data points are equally likely to be above or below the line, the curve. Those blue data points are now different only by random residuals from the fitted values, whereas when I use the line that was not a parabola, but just a line, and for these post-1960 fast data points, well, either they were usually above the line or they were usually below the line, and that's because I was missing the curvature. So that looks much better. I see the same thing for these 3 orange kites, right? These ones used to all have negative residuals. That's no good. Now they're clearly centered at 0 approximately. You could say they still have smaller variance than maybe the residuals for the fast group, and that would be a valid thing to say. You could also argue there's only 3 of them, but you know, that could be a valid concern that there might be less variance among the slow post-1960 data points than the fast ones, right? That's certainly true. And the thing I like about all of the pre-1960 dots is that there's no more curvature, right? So if you look at the orange filled in dots, right, they are now randomly dispersed above and below the line. Look at the blue dots, randomly dispersed above and below the line, and they are no longer usually above or usually below. So this is a much better residual versus fitted value plot, just like this is a much better scatter plot. So you get used to this. It's a skill to build, being able to use visualizations to help you choose a model. The last thing I want to do here is show how the measures of model fit that we've discussed might contribute to choosing a model. So first of all, I didn't list this in the measures of model fit, but note that the residual variance itself, of course, is one measure of model fit. It doesn't take into account the number of parameters, but it does take into account the residuals, right? So the residual variance, if I compare model 1, which was the 2 lines with the interaction, to model 2, which is the 2 curves, again, allowing interaction, you can just see that the residuals get way smaller, right? The residual variance gets way smaller because the residuals get way smaller when I include the parabola, when I include the squared term. So that alone tells you a lot. That is a big dip, right? To go from 22 to 16. I'm not saying it's a big dip based on any kind of technical calculation. I just note that the number 16 is a bunch smaller than the number 22. Also, I could look at the R squared that I'd get when running each of those models, and I can see it goes from 74% to 82%, right? So instead of describing, with the lines can describe 72% of the variation in speed using track condition and year, but the second model can describe 82%, and that's a nice increase. You can also look at adjusted R squared. Now here, as in many cases, adjusted R squared is very similar to R squared. That's a good thing. That tells us we're not in danger of overfitting. The number of parameters is nowhere near the number of data points. So that is a very good thing. But as is usual, the adjusted R squares are a little bit lower than the R squares. And you can see that they're more similar for model 1 than they are for model 2. And that's because every time we add new terms to the model, R squared just greedily, hungrily gets bigger, and adjusted R squared is not going to get bigger as fast. But still, it got bigger, right? And the fact that adjusted R squared got bigger just like R squared got bigger suggests that we are reducing the residuals and perhaps not at the expense of overfitting. You can also look at BIC and AIC. Now, BIC and AIC are not going to be interpretable in the same way that R squared or even sigma hat squared is. You're not supposed to look at this number 172 and infer anything. What you are supposed to do is compare the BIC from model 1 to the BIC from model 2 and say, hey, it got smaller. And that suggests that the second model is a better choice than the first model. Remember, the BIC is taking into account both the residuals and how many parameters you had to put into the model to reduce those residuals. If you had to put in a lot of parameters in order to get smaller residuals, then the BIC won't reduce, right? Or if you have a very sparse model, only a few predictors, but it didn't help with the residuals, BIC won't get smaller. So the fact that BIC is just a smaller number here, and again, it's using knowledge of numbers, not any technical calculation, 140 is a bunch smaller than 172. That tells me the residuals did get smaller, and the number of extra parameters I had to include wasn't harmful here. It wasn't so many, right? So instead of, let's look at these models again. Here it was 1, 2, 3, 4 betas I had to estimate. This time it was 1, 2, 3, 4, 5, 6. So I went from 4 to 6 betas, right? But the residuals dropped a bunch, and so this measure is telling me it was worth it. AIC is doing exactly the same thing. Just like with BIC, you're not supposed to try to interpret this number 158. You're just supposed to compare it to the AIC you'd get with the other model, and you see that it is a bunch smaller, and therefore perhaps the trade-off is worth it. Perhaps having these extra 2 parameters in the model is worthwhile and does not put us at risk at overfitting, maybe because we did have a substantial reduction in the residuals. So when you are choosing a model, you need to balance all these things. You need to use your exploration of the data. You need to use your knowledge of the context, which variables might actually matter. You can use your model selection criteria, but don't use them blindly. There are some methods out there, there's one called step selection, that will check every possible model and report back the one with the smallest AIC or something like that. Don't use those, right? Don't use those, because if you look hard enough, you'll find whatever it is you think you're looking for, right? Even if you use an algorithm like that, they err on the side of overfitting, right? If you try every possible model and report back the model that just has the smallest AIC of every possible combination of predictors you could use, you're going to end up with a model that describes the data, the specific data set you have too well, usually. It's better to use your knowledge of the context and your understanding of the visualizations of the data to propose a couple models, and then maybe use additional visualizations plus these measures of model fit to help you choose a model that you think is the best one. And then ideally you've saved a little data for later to do cross-validation.